I am Professor Nagaraju, Computer Science and Engineering, YSR Engineering College of Yogamana University, Prodhutur. So I was the first batch student of JNTU Anantapur, 89 to 93. So today I am going to discuss about semantic analysis. Semantic analysis. The today's session contents are introduction to semantic analysis. So syntax directed definitions, evolution order of syntax directed definitions. So syntax directed translation, applications of syntax directed translation, and gate problems and solutions. So these are the today's contents. So first I will give the introduction about the semantic analyzer. So that is the semantic analysis. That is the semantic analysis is the third phase of the compiler. Semantic analysis is the third phase of the compiler. It uses the syntax tree and symbol table to check whether the given program is semantically consistent with the language definition or not. The main objective of that semantic analysis or semantic analyzer is it uses syntax tree and symbol table to check whether the given program is semantically consistent with the language definition or not. So semantic means it provides the meaning. So it gathers type information and stores it in either syntax tree or symbol tables. It gathers type information, that is the data type information, and stores it in either syntax tree or symbol table. What are the main functions of that syntactic analysis? What are the main main functions of the semantic phase? So first one is the type checking. So that means here is every variable it will verify that either what kind of variable it is, either data type, either that is the integer, character, float, or double or string. So that is the compatibility of the variable will be checking. So in the semantic section. So that is the next label checking. So that means for each and every statement they can give some labels, or suppose that is the pointer values or something. So those label checking in the symbol table or syntax tree. So it will be verifying. And flow of control checking. It is also verifying flow of control checking of iterative statements or functions or decision making statements like that. So if there is any syntax say errors, so semantic errors, so it will send the semantic errors to the error handling tables. So semantic errors, some of the semantic errors are type mismatching. So for example, in the program, so in the calling program, so we are assigning the variable is integer, and in function we are returning the values is float. So then whenever I am using this kind of this kind of statements, it will display the type mismatch. Or sometimes that is undeclared variable. Sometimes we can use the variables within the program or within the statement without declaring in the declaration part. So before going to use any variable, you have to declare in the declaration part. So for example, in the C programming like this. So like this. So next one is reserved identifier misuse. So generally the reserved words or keywords cannot be used as a variable. Sometimes suppose if a reserved word is declared as a variable, so definitely it will display the errors. These errors can be sent to the semantic, so that is the error handling tables. So for example, you see that, so from beginning to, so that is the semantic tree what we are doing. So first to program, suppose here is the first you see that a program statement. So that is we are taking 5 plus 7 into x within the bracket. First this will be sent to the lexical analyzer. So here in the lexical analyzer, divide that program, that statement into number of tokens. That means a stream of tokens. These stream of tokens will be given to the parser. Stream of tokens are given to the parser. That is the second phase. So in this parser uses this, suppose here is how that will be dividing the tokens into tokens. So by taking the regular expressions and regular grammars. So after that, so these tokens will be sent to the parser. The parser uses context-free grammar and construct the parse trees, and based on the parse tree, it will verify either syntactically the statement is correct or not. So that means here that syntactically either the statement is correct or not. So already I explained some algorithms, top-down approaches, top-down parse trees or bottom-up parse trees like that, right? So after that, so the parse tree will send to the syntax. Suppose here is, if there any errors in the parse tree, it will send to the error. It considers the syntax tree. But here is we are taking number 5, number 7, number I. So number ID X. So, but here is, but when you are taking that, so this syntactic, so that is this parse tree is sent to the semantic phase, that is the semantic analyzer. But here is, if we then find out any semantic errors, it will send to the error handling table. Otherwise, it provides the meaning for each and every identifier and attributes. It is an abstract syntax tree. So that means here is, so in this class I will explain that, so what is the main function of that one, how it will check the type checking or type checking or type mismatch, so that is how it will be performing. So that is, here is the first, before that we will see that syntax direct definitions. So here is the one thing is, suppose here is, so that is the syntax trees. Here is we can use syntax trees. So in the syntax analyzer, we are using the parse tree, and here is we are using syntax tree. So what do we mean by syntax tree? Syntax tree is equal to parse tree plus additional information. So syntax tree is equal to, so parse tree plus additional information. That means for the any parse tree, if you add some additional information, it will become a syntax tree. What is the additional information? Additional information may be attributes, rules, or actions, etc. That is, additional information may be, so that is the attributes, rules, or actions. So suppose there we are taking there some non-terminals like this. Suppose here it is SDD. SDD means syntax directed definitions. SDD is a context-free grammar with attributes and values. Here is also the syntax tree uses the SDD is a context-free grammar with attributes and rules. So this is called, so context-free sensitive grammar. Context-sensitive grammar. That means here is syntax-directed trees are using. So that is a context-sensitive free grammar. That means, so for any context-free grammar, so with the attributes and rules, so that is called the context-sensitive free grammar. Attributes are associated with the grammar rules. So here is the, when you are using the attributes are associated with the grammar rules. That is not a grammar symbol. So means that is the non-terminal symbols, and rules associated with the products. Suppose the grammar symbol means that is so the terminal nodes, terminal symbols, and rules with the productions. That means here is the production. Suppose E is equal to E tends to E plus E, like that, the productions, right? So that means attributes are associated with the grammar symbols and rules with the productions. So for example, each attribute has a well-defined domain of values. But when you are taking that attribute, suppose when you are taking, suppose, so anything you can take the attributes of that. Suppose here is the value, size, or maximum, like that. No? So each attribute has a well-defined values such as integer, float, character, string, and expressions. But within the program, when we are using the attributes or identifier, suppose we have taken ABC or the three variables. But what kind of data we are giving, either integer, character, or float. But in the syntax tree, so it doesn't bother about what kind of data type values you are giving. It gives the generalized expressions. But here is for each and every variable, so it assigns some data type, either integer, character, or the same thing. In the same way, while executing the expression, so that expression is also, so that is make it as a meaningful. So that is, suppose here is, what is the difference between suppose context-free grammar and context-sensitive grammar means? But here is, suppose when you are using this in the production, you see that it is a well-known, E tends to E1 plus E. Generally, we can use E tends to E plus T. So in the syntax tree. But here is, so suppose the two cannot make like same thing, same variables. That means here is, if two variables are there, there may be some ambiguity. To avoid that ambiguity, so here is we are using E tends to E1 plus T. And for this one, we are adding some semantic rules. That is the semantic rules we are adding. So this is the production. For this production, we are adding some semantic rule. E dot code, E1 dot code, or T dot code, or plus. So that means here is that when you are using this some meaning. So suppose it is a E is a code and E is a code, or suppose if we are given that here is the value, we can say that it is a value or something. So that means we are providing some meaning. So that a dot code is a attribute. Here is we can say that a dot code so can be represented with the attribute. Or sometimes suppose the semantic tree, if we want to print the values, we can use the actions. So we may also insert the semantic actions inside the grammar. For example, if it is a final node, suppose E tends to E1 plus T, and suppose print it is a, so suppose a terminal node, so it is a terminal node. So terminal node means print, we can print the plus. Suppose if you want to print the plus, it is added to this. This one is called action. The action is added within the curly braces for the statement. Right? This is the syntax tree, right? So, but when you are using the syntax tree, in this case, we can follow only two things. One is the syntax directed definitions, and another one is the syntax directed translation. So, syntax directed definitions means here is, so we can assign some meaning to the expressions or data types. So that means here is whatever we are taking. So then expression. Suppose there is some expressions we are taking. So that's why. So next translation means, so the same thing will be, so that is translated into intermediate form of the language. So that is in this class I will explain how to, so that is define the syntax directed definition and the syntax directed translation. For example, you see that syntax tree, just only I will explain the differences between syntax tree and parse tree. Suppose syntax trees are abstract or compact representation of parse tree. So syntax trees are abstract or compact representation of parse tree. That is, syntax trees are called abstract syntax trees. Suppose abstraction means because they do not provide every characteristic information from the real syntax. That means here is simply it will provide, that is higher levels. Only it won't provide in detail description about the statements or data types or like that. For example, here is when you are using that in the syntactic in the syntax in the parse tree, we should follow some rules and regulations. Suppose you have to follow the rule node or no parenthesis, but there we have to represent the parenthesis, and at the same thing you have to follow the rules. But in the syntax tree, you need not to follow the rule nodes. For that nodes, you need not to follow any rules and no parentheses. Suppose in the syntax tree, there is no parentheses are specified, right? So that is the main differences. You see that, so the main differences of parse tree and the syntax tree. Parse tree is a graphical representation of the replacement process in a derivation. For example, when you are taking the parse tree is a graphical representation of the process of the derivation. Either we can either leftmost derivation or we can use the rightmost derivation. So that means for how we are deriving the expressions or how we are calculating the values, that will be expressed by using parse trees. So syntax tree is a compact form of the parse tree. So here is the, so that is already we don't know. So that is we want to provide in detail description about syntax tree. Each interior node represents a grammar rule. But here is, so that is the tree contains root node, internal node and leaf nodes. So that means in the parse tree, that is the root node, all internal nodes that represent the grammar rule. Each interior node represents a grammar rule. That means a production. That is the non-terminal nodes. And each leaf node represents a terminal. Each leaf node represents a terminal. But in the syntax tree, each interior node represents an operator. Each interior node represents an operator. And each leaf node represents an operand. But here is the leaf nodes are operands, and that is the internal nodes are always, that is the operators. Either that is the arithmetic operators, relational operator, any kind of operator. So third difference is parse tree provides every characteristic information from the real syntax. Real syntax. But here a syntax tree do not provide every characteristic information from the real syntax. But here is suppose when you are constructing the parse tree, so you should know you must be so you must not violate if the expression having the parenthesis. But here is you can remove the parenthesis in the syntax tree. So next one, parse trees are comparatively less dense than syntax trees. Parse trees are comparatively less dense than syntax trees. But syntax trees are comparatively more dense than parse trees. But here is suppose this is abstraction. That's why so internally it will be more common. These are the differences between these two. But here is suppose when you are using that is a syntax trees. So we can use the dependency graphs. Another one is the annotation tree. Annotated parse tree. So that means here is the dependency graph. So what is the use of the dependency graph? The dependency graph is a tool which will specify the order of evolution of expressions. So that is the dependency graph, and the useful tool for determining an evaluation order for the attribute instances in a given parse tree. So that means when you are given the parse tree, it specifies that, so that is the which operation should be executed first. That is the associativity and precedency will be specified by using the dependency graph. So that is annotated graph, annotated parse tree. So here is when you are using that annotated parse tree, it shows the values of array. Annotated parse tree means if the syntax tree contains, so that is the values. If the syntax tree contains the values, that is called annotated tree. So that means, so that is the syntax tree. So with the specified values is called, so that is node values. We can call it as a annotated parse tree. A dependency graph helps us to determine how those values can be computed. With the help of that dependency graphs, we know that how the values are computing, how we are getting the answer like this. So, for example, you see this example, annotated tree. What do you mean by annotated parse tree? So that is the parse tree with the values. The parse tree with the values, that is called annotated parse tree. So for example, here is you take the grammar. So suppose here is this side, left side is the context-free grammar. We are using left side is a context-free grammar, and right side we are using semantic. So that is the grammar. Semantic rules we are providing. So that is already we know that. So we have done so many graphs. So that is the parse trees for this grammar. So for this grammar, just so that is the top we can use en, L is equal to un. That is the one production rule can be implemented. We can say that it is a final state. But so that is in the previous, suppose in the LR parsers, already I explained that. So we have to take one accepted node. But here is also whenever that reads it to this one, it prints the e value. Whatever value is getting, that e value is received. So here is suppose in this case, so this context-free grammar, we are making it as a semantic, that is the context-sensitive grammar. So e dot value is equal to e1 dot value plus t dot value. So that is e dot value is equal to t dot value. T dot value is equal to t1 dot value into f dot value. And here is t dot value is equal to f dot value. F dot value is equal to e dot value. So that means here is f tends to digit. Finally, we can use the identifier. F dot value is equal to digit dot lex value. Lex value means either it may be either integer value. The lex may be either integer value. That means we are taking the value of this. So by taking this grammar, so here is the given expression is that 3 into 5 plus n. So either you have to say that either the given expression is accepted or not, either it will be correct or not, or what value it will be generated. So, but in the previous case also we have written, but here is when you are taking that is the brackets within a capital E within the bracket, but here is we can't see the bracket anywhere. But in this case, annotated parse tree means, so first we can construct the parse tree. We can construct the parse tree. So that is after constructing the parse tree. So then, so each and every value, each and every, so that is non-terminal or non-terminal value can be replaced with the added with the attribute like E dot value. So E dot value, T dot value, T dot value, T dot value, T dot value like this. So here is we are taking this is the one capital E is equal to for this one. First we are replacing E is equal to E plus T. E is equal to E plus T. So then here is value. Next after that, so that is the star is there. So that's this E is replaced with so that is T1 star FE. So then FE T is replaced with F is replaced with the digit lex value. So for example, in this case, and here is, you see that 3, 5, 4, n means it is accepted state like that, right? So that is, so first we are taking that digit dot lex value is equal to 3, and here is initially we can digit dot lex value is 5, and digit dot lex value is 4, because according to, so that is the parse trees, the syntax trees. So here is, so how the annotated parse tree will be evaluating. So that is evaluating. Suppose here is, so it uses the top down parsers or bottom up parsers. But when you are using it in a top down parser, it reaches leftmost derivation. It will be evaluating with the leftmost derivation. It will evaluating with the leftmost derivation. Suppose here is, so first one is that will come through like this. Suppose here is, so that is the, so then here is it comes like this, and here is that leftmost derivation it will take, and the next that will be evaluation should be like this. So suppose here is when you are using that, so it will consider the evaluation of, so this process, or so suppose this is the process like this, or next this one, so next this value. So suppose here is itself 2, and this, or next that one is the value of this one. So here is the tree will be evaluating like this. So then here is the first, you see that here is the when you are using that. So first that is the first value it will be taking. Suppose here is, but when you see that first here is that will be taking this value of this. Suppose here is digit dot value, and here is digit dot value is, so that is this value. So f dot value is replaced with 3. That means here is reduction. It will do the reducing parser. Either is the same thing we can use. So but here is in the top down parsers also we can use, but at both the cases we can get the same results. But here is, but when you are using the top down parser, so this is replaced with f dot value is equal to this is replacing. So next t date value is replaced with reduced by f dot value. So then here is t dot value is, so that is replacing with the 15, right? So but here, so instead of that, here is the bracket is star is there, again that will comes to this, and 5, and here is a 5 f dot, and here is this one will be multiplied 3 into 5, that is equal to 15. So here is the t dot value is equal to 15. This t dot value is replaced with the root node of this, e dot value is 15. So after that it will comes to this place in where t dot, so suppose here is digit dot value is 4. So 4 is come to the 4 dot value, f dot value is equal to 4, t dot value is equal to 4, and these two will be added, and so that is the 15 plus 4 is equal to 19. So after that this value is assigned to L. So then in the L case, suppose here is you are getting L means, suppose here is when you are getting that L, so that is it is a accepting state, and here is N we are getting, so 9n we can use the value of this. So this is the evaluation procedure from top to bottom. But the same thing, suppose you can use the, so suppose the same thing you can use bottom up parser. Suppose here is a bottom up parsers means here is the first these two values, wherever the reduction is replacing. So suppose that is also we can take the leftmost derivation, and from the last value, suppose here is in the so that is the post order evaluation it will be taking. So in the post order evaluation, that is the first left subtree and right subtree, after that node will be performing. Whenever the node is replacing, so then that will be making the values. So but so suppose in this case we are using rightmost derivation, but when we are using this bottom up approach, so we can use the stack operations like this. Stack operations we can use, so that we can, that is the depth first search, that is the depth first, so that is the graph searching can be used in the case of that dependence. So later on I will explain how to get. So suppose I have understood that this is the context free grammar, this is the by adding semantic rules it become a context sensitive grammar, and with the values of this we can derive the first parse tree. So for that parse tree we can convert that into the syntax tree by giving the semantic values. So after that, by assigning some values for identifier, we can make it as a annotated tree, parse tree. That is annotated parse tree means that parse tree with the values or syntax tree with the values. So then we are evaluating and we are getting the answer like this. So that is, have you understood that? This is the annotation. So next, suppose the same thing when you are using the dependency graph example, but it will specify the evolution order of this one. This will be specified evolution order of this. For example, so but in this tree, this only we are using the lines without directions. But here is we are using the directed edges. We are using directed edges. So for example, when you see that here is, so but they are 5 plus 3 into 4. Suppose if you have taken that 5 plus 4 into 3, and here is also using that leftmost derivation, and next that is using the stack operations like that. Suppose this is dot 5. So then arrow mark is showing. That means here is, so the direction, the evolution procedure will be starting from leaf node to, so that is the root node like this. Only that is the difference. But a dependency graph does not contain any cycle, so that is called a cyclic graph. It is a dependency graph. It specifies so how the values are getting. For example, here you see that, so that is the evolution should be from bottom to top up to this, after that that is up to this, and next to this one, and the values will be performing, and so that here is that will be executed. But here is that is the dependency graph. Later on we will go into about dependency graphs under this one, how that will be specified, right? So for example, if we are given like this, construct the syntax tree for expression. So A into B into C like this. Suppose simply we can construct like this. First one is you can take this to A, B, a star and C. So that means you see that all the leaf nodes are identifiers or terminal nodes, all internal nodes are operators. So in the syntax tree, that is in the syntax tree, so that is here is up, so that is here is internal nodes are star. But here is, suppose when you are implementing this by using tree structure, so we know that left subtree, right subtree like this. This is the left subtree, and two nodes we can get, and we can assign the value of this. So, but constructing the syntax tree for the same thing. So, suppose here is, suppose when you are using this pointer, the t dot pointer we are using t dot pointer, e dot n pointers. That is the pointer variable. When you are assigning, here is the attribute is assigning the pointer. So then here is the same thing can be implemented by using this. So that is a very interesting. So that is very interesting and very important. So that is the function is. Suppose you see that. Suppose in the general in high level language, how the statement will be checking. Suppose we have the following code. If x less than 0, then x is equal to 3 star within the braces y plus 1 star comma else y is equal to y plus 1. So it is a, then means it is in the Pascal expression. That is in the Pascal programming language. We can use if x is less than the less than statement, else greater than this one. Else that statement we can use. But here this if statement contains if, and here is left braces, expression, relational operator like this. But how do you represent this by using? So that is the parse tree. First we can use the construct the parse tree. After that we can convert that into syntax tree. So suppose you see that first it is a statement. So that is the if is a statement. So that is statement we are using if expression, then statement, else expression, then statement. So you see that parse tree expression may be contains identifier, relational operator or number. That means A is greater than A, or like this, A is greater than A. That means here is very number. Or you can use also, you can also use this one is also identifier, no problem. So expression, ID, relational operator or number. But here is in this statement again we see that expression id is equal to expression. Id is equal to expression. Here you see that this expression id is equal to id expression and else part. So that is expression may be so expression star expression. Expression star expression that is within that. So that is the y plus 1 we are taking. That is the expression we are writing. This expression plus that is the y plus 1 we are written. But this is the so that is the if part and the same thing. Suppose if you are taken that I numbers like this. Only this is if part and this is the else part of the statement. So suppose if expression then statement else expression. In the else part we can write identifier equal to expression. So then this is the so suppose when you are saying that it is a parse tree, but here is you see that in the parse tree, suppose id relational operator number we are using, but when you are using relational operator means what is the relational operator? So here is also we are using the brackets, right? That means we are giving, so that is a priority of the priority of execution of the expression. So that means here is, so that is where now we are following the associativity and the precedency of the operators. So for the same thing, you write a simplified version of this. Here is we are writing syntax tree. So that simply we can use if expression then statement else statement. And here is expression may be x is less than 0, x is less than 0, same as it is you are written, and the statement that is id is equal to id star id plus id, that is a y into y plus I something we are written there. So that is the else statement we can write id identifier is equal to plus identifier and a number. This identifier is like this. But this is the syntax tree. But when you are taking that, this is the abstraction. This is the abstraction. But we are now only it can be used for only for a specific. But you can't see. Suppose if you are good at C programming or if you are computer science, you know that it is a less than is a relational operator. So, but outside people cannot understand this what it is. That's why here is it provides the more abstraction than parse tree. So here is you see the syntax tree A is equal to B star minus C plus D star this one. Suppose here is same syntax tree we can assign. So that is here is we are mentioning that so directed graph also we can dependency graph also we can how that will be evaluating of this lower level of this. So just you see that one example. So one example. So example of syntax tree. Suppose you consider the following grammar. E can have the form of E plus T or T. T can have the form of T into F or F. F can have the form of E within the bracket of this. So for this one, you consider for the given string ID plus ID into ID. This is the for given string. So draw the parse tree, syntax tree, and a direct and acyclic graph. So for this one, already we have written syntax graph. First you take that. So first root node, that is the root is E. I have top down parser. E can replace with the production of E plus T. E plus T because there is the first one is the plus is there. And the next here is this T is this E is replaced with the T, and the T is replacing with the F. F is replaced with the ID. That means here is so we have the productions will becomes like this. After that here is star is there. Suppose there is the star, you have to so this one this product you have to use, this production you have to use. That is here is the T can be replaced with the T star F production, and the next F is your ID. So that is the T replaced ID or this one. This is the parse tree. When using that, this is the parse tree, and here is annotated tree. That is the we are using directly. That is syntax tree is with annotation. Simply, so just we are in the ID plus ID star ID. So then you see that how much abstraction is there in the syntax graph. But here is every production we are representing in the parse tree. But here is everything is abstracted and only we are using the expressions in the high level. So that, but sometimes suppose when you are using that three, if more than one, so that is the duplications are there. So it will be removed by using the direct acyclic graph. So suppose all the stars and this will be used to the identity. This is the directed cyclic graph. Later I will explain this cyclic in the graph in the intermediate code generation. So I will show that. But here is, so this is the expression. For example, when you are given the construction of parts T for the given expression. For example, so suppose in the C programming, when you are assigning the statement like this, suppose when you are given, so X is equal to the statement A plus B into C minus D plus E by F and A plus B. But when you are using the statement, you have to evaluate the tree. So then already we know that, so suppose in the evaluation, already you have studied that is the postfix expression. So that is the, suppose whatever you are given the programming language in infix notation, first it will convert that into postfix notation. Why it is converting means, the in the postfix notation, it doesn't follow any rules and any priorities. That means it doesn't accept any braces, or so it doesn't process any priority of operators. So that is all are equal. So that's why it is very easy to construct. For example, you see that, so that is the first thing is, we have to whatever taken the input expression, this will be converted into postfix expression. But even in the C compilers also, so the same procedure, whatever are given the input expression, first the compiler will be in the semantic analyzer, it converts that into, so that is the postfix notation, then only, so it will convert into intermediate. Evaluation should be very easy for finding the error. Evaluation. Suppose here is we are taking this, but you can use the stack, but here is without using the stack, directly I am writing this, but you can use, but here is when you are using the expression, braces are there. So that means highest priority will be given to the water. So brackets. Or here is the star and plus, and here is the brackets also there. So that's why we can take this expression. So the first one is we can calculate. So first one is we can calculate this one. Suppose here is we are taking this. So first we are taking this. So then here is A plus B, because here is, so but plus operator precedence is lesser, but even though that is included in the braces will take highest precedence. So first that will be. So in the postfix expression, they will write like this, AB plus we can write like this. This is, we can write AB plus. Or after that, so again here is the bracket is there. Again here is we are using braces. So that's why second it will convert. So that is the CD minus. It will convert CD minus, and here is that is the, actually this is a converted CD minus. And the next one is, suppose here is AB plus this one, and the minus is there, the plus, and again here is a internal. So suppose within the bracket, that's why it will be evaluating. So here is the plus is there, and so division is there. Suppose the first division will be performing first. This is the third case. So next after that, this will be performing. So suppose here is we are taking, so that is the value of this one. So then it will be A minus D. So here is the next AB plus and CD plus EDF you got. So next after that, because here is this is the 1 and this is considered as a whole is a A, and this A is considered as a whole is a B. So then here is again star is there, and the next here is we are taking, this is entire, suppose here is we are taking, so entire thing is like this. So then here is the star and plus, first preference will be given to star. So then here is, so that will be writing, this is the A and this is the B like this. So entire thing it will be taking values. So then it will be converting and plus, and next we are assuming that it is, again it is in the form of A plus B. It is A plus B. So then here is, again we will make it as this plus will comes and last. So this is the postfix expression. That means with using stack or by using any, so that is here is by using postfix order, so that is the post order to ourselves. So then we can convert the tree into, so that is the into postfix expression. So after that, how with the help of this postfix expression, so we can evaluate the process. Already we know that. So suppose here is the stack is there, we can use the stack. So with the help of the stack, we can evaluate the process like this. Plus A, R plus A, R plus A, like suppose if two operands are there, we can push onto the stack. So from this left to right, so like A and B pushing onto the stack, and next whenever the plus is comes, so these two will be pop and make it as a operation, that is A plus B. So after that we can push C and D and minus, but when it comes minus, it will write the C minus D. So next when you are pushing the start, so this is here is the same as it is. You see that there are no precedency of operator, there is no brackets. Only from left to right we are pushing all the values into the stack and we are evaluating. Suppose whenever the find the operator, so we are pressing like this, and here is a star and next division. So then it will be take place and E by F, or next one is we can use like this. We can evaluate the expression by using stack. I think you are all familiar with this, so that's why I did not take any value. But the same thing we can construct the syntax tree. But for the same thing we can construct the syntax tree like this. How we are going to construct the syntax tree means, so that is the last one is the root node. Last one is the T is a root node, and here is the plus and the pluses are there. Suppose this one is the for this one it is a last. For this one, this star is a last. That means here is the node should be always. So that is the so that is the left subtree, right subtree node will be visited in there. So that's why here is. So first it will take the plus, and next in this case, suppose when you are taking that, suppose here is this is the for this symbol. It is the plus and this. So then here is we can take the value star and star plus plus ABC ABC like this. But when you are constructing tree like this, when you are constructing this tree, so with the postfix expression, so automatically it will be finding the value. Suppose if you are given A is equal to, suppose in this case, suppose A is equal to, if you are given 2 and here is the 3 and here is the 4 and suppose here is the 5 and like this 5 1 1. So here is again 2 we are taking, that is the 2, or next like this, suppose the B is a 3 like this. When you are given that, so suppose here is a 2 plus 3, so then here is it will write 5. This node it will write 5. And here is a C plus 5, C 4 plus, so 4 minus 5, that is equal to minus 1 it writes. So again it will calculate minus 1, that is equal to, so that is the minus into, sorry, 5 minus 1 into is equal to minus 5. Here is we are getting minus 5. And next here is the post. So next that will comes to this place and it will take the E value. So suppose E 1 and the next F1. So that is a 1 by 1 is you are getting 1. 1 by 1 is equal to 1. And here is a 2, 3 that is equal to 5. And 1 into 5 that is equal to 5. And next here is a plus means here is you can get to 0. So that is the minus, that is the minus 5 plus 5 is equal to 0. So that is with the help of syntax directed tree, so we can eliminate the values like this. So I think I have understood that. So this is the evaluation. That means we can take the expression, so we can convert, we can make it as a parse tree, and that annotated tree directly we can apply the post ordering. So that is a post order traversing, so that automatically you can get the values. But here is you need not to use any stack operations. So the simple thing is in annotation tree. So that is we can eliminate the we can construct the parse tree. And after that we can enter syntax tree, annotation tree. So in annotation tree is, so that is the traversing in the post order, so then you can get the answer. So that is the stack means you need, suppose in the stack when you are using the recursive procedure again you have to follow. So that is the syntax directed tree translation. So for the same grammar we are given 2 plus 3 star 4 that is equal to, here is we are given. So the same grammar, this is the syntax tree. And the evaluation should be from topmost to, so that is the rightmost derivations like this, and next that will be evaluating, and so that it will be getting the values. Here is the, for the same grammar, suppose here is taken the grammar is this one, this is the context B grammar, E tends to E plus T or T value, E dot value is equal to E dot value plus T dot value, E dot value is equal to T dot value, and here is also we can use the same as the data context sensitive grammar, and here is we are constructing that evaluation procedure will be done like this. So next concrete tree and abstract tree of this one, that is same. So suppose when you see that here is everything is represented, F, T, all productions, but here is a no production is represented. So that's why it is abstract tree and it is a concrete tree of this one. So concrete parts trees are same thing like this. So that is this is the concrete, and here is we are using the representation of tree representation, and it is the evolution procedure we are using. So next I think I have understood that. So what is the parse tree, what is the syntax tree, and what is the annotation tree. So that is how we are going to evaluate the expressions by constructing the graphs, that is the things. So then here is why we are using that, but we have to follow the some rules and regulations. That means here is, so that is attributes we are assigning. Attributes means we are assigning attributes to the terminals, and rules for productions. That means a tree is, so that is the part syntax tree is equal to parse tree plus some additional information. That additional information may be attribute or rules. Attributes are assigning to the terminal nodes, and the next that is rules are assigning to, so that is the productions. But how that is the, so then here is how to make it, so that is how the attributes, suppose how attributes will be evaluating. So for that purpose we can use some special grammar, that is attribute grammar. So here is we can use the attribute grammar. So what type of attributes we can use in the syntax parse tree? So syntax tree. So that is attribute grammar is a special form of context-free grammar. Attribute grammar is a special form of context-free grammar where some additional information is appended to one or more of its non-terminal in order to provide context-sensitive grammar. It means the attribute grammar is a special form of context-free grammar where some additional information is appended to one or more of its non-terminal in order to provide context-sensitive information. Each attribute has well-defined domain of values such as integer, float, character, string, and expressions. So that means here is when you have to assign. Suppose if you are using that, so A is equal to B plus C. So suppose if 3 are integers or 3 are float, we can calculate. Suppose A, B are integers and C is a string, then it is not possible to execute like this. But here is attribute grammar is a medium to provide semantic to the context-free grammar, and it can help specifying the syntax semantic of the programming. It is the medium between the context-free grammar and the intermediate course. Attribute grammars can pass values or information among the nodes of the tree. So suppose for each and every node it represents the production, or so suppose value operator. So automatically it provides some rules and regulations of this. For example, you see this grammar. So E tends to E plus T, or E dot value is equal to E1 dot value plus T dot value. So here is the right, suppose you see that the right part is a context-free grammar, and here is after adding that we are adding some semantic rules to this one. So but here is when here can be assigned values of this one, that is semantic attributes may be assigned their value for their domain name. Suppose here is, but these attributes, but when you are using these attributes, so these attributes, that is these attributes will be classified into two categories. One is synthesized attribute and another one is the inherited attributes. Synthesized attributes and inherited attributes. So these attributes, that is based on how they are evaluating, either the node is calculating the node value is calculating by taking the values from its children or by taking the value it's from parent. Based on that, these attributes are divided into two categories. One is the synthesized attributes and another one is the inherited attributes. These are important. Synthesized attributes and another one is the inherited attributes. Right? So that means the attributes may be classified into two categories. One is the synthesized attributes and another one is the inherited attributes. So now first we will study about, so that is the synthesized attributes. Now study synthesized attributes. So synthesized attribute is an attribute of a non-terminal on left hand side of the productions with the semantic rules. A synthesized attribute is an attribute of a non-terminal on the left hand side of the production with semantic rules. Here is some semantic rules we can provide. The attribute can take value only from its children. Suppose if the attribute is taking value from its children, that is called, so S attributes are synthesized attributes. So synthesized attributes means, so that means it taking, that is the attribute which take the value only from its children and value itself. That means the and its value, that is the attribute can take the values only from its children or and that node value. So suppose here is, sometimes you can use C is equal to C plus A plus B like this, but here is when you are taking the previous initial value can be added, that is even. So that is I want to say that synthesized attributes, or you can call it as a S attributes. The attributes which can take the values from only its children and its value, that is called synthesized attributes. For example, you see that say A can have the form of B in BC is a projection of grammar, and A attribute is depends on B's attributes or C attributes. That means the A attributes are depending on B's attributes and C attributes. Then it will be synthesized. So because it is a root node and these are the children. That means if you want to find out the value of A, so you must calculate the value of B and C. That's why. So that is, this is called synthesized attribute. Have you understood that? So here you see that A is calculated with the children B, C, D values. So then we can call it as a synthesized attribute. Now you see that. So examples of S attributed SDD. So that is how to define S attributed means synthesized. S means here is synthesized attributes. So that is the prediction or semantic rule. So this is the predictions we are using, and we are adding the semantic rule same as it is. That is already we have studied. So the S attribute, so that is the syntax directed translation. So how that S attributes are translated into intermediate form after. If an SDT uses only synthesized attributes, it is called as a S attributed. So the syntax directed translation. So that is the SDT means syntax directed translation. SDT means that is the definition. Syntax directed definition, and here is the syntax directed translation. So that is the syntax directed definition will give the meaning and information or evaluation procedure for the tree, syntax tree. But here is it will translate it into other form, either that is the intermediate form, either the intermediate code or something like STD. So S attributed, so that means if SDT means, so the syntax directed translation, when you say that if the tree that contains only S attributes, that means if SDT uses only synthesized attributes, it is called as a S attributed tree. So S attributed SDTs are evaluated in bottom-up parsing. But when you are using the S attributes, for example, in the parse tree we have studied, that is the top-down parsers and bottom-up parsers. But so that is the top-down parsers may suffer with some problems. That is the left recursion, left factoring, or ambiguity. But here is in the right. In the bottom-up parser, there is no left recursion or something. Suppose that ambiguity grammar also we can eliminate sometimes in the bottom-up parsers, right? So that is, but in this case also, that's why either which parsing techniques you have to use. So that is the based on this attribute. Suppose S attributes means here is maximum S attributes are evaluated in bottom-up parsing, as the value of the parent nodes depend upon the value of its children. Because the bottom-up parsers means it takes the values of at the leaf level, it evaluates from bottom to top in the rightmost derivation, it's the reverse. So that's why here is S attributes. When you are using the S attributes, it follows the bottom-up parsers. The semantic actions are placed in rightmost place of RSS. So that is the, for example, here is when you see that prediction or semantic rules. So the same thing we are using. Now you see that evaluation of SSD at the node of the parse tree. So the same tree we are taking with synthesized attributes, we can evaluate attributes in any bottom up order. That means we can use the any bottom up parsers like this. Suppose here is LR parsers, SLR parser, LAR LR parser, or CLR parser. Such as that post order traversal of the parse tree. So it uses the bottom up parsers and evaluation should be in post order. So the post order traversals. So here is you see that value and lex value means that is the integer value or synthesized attributes. So for this grammar, here is we have drawn the annotated parse tree, and here is suppose the evaluation that should be so from top to bottom to top. So suppose here is how that will be evaluating means. So first that comes to this place, and here is that start with digit dot value is equal to 3, and the next one is it takes the f dot value is 3, t dot value is 3, and here is d dot value and f dot value. So then here is, so you take the operator, so 3 into 5, 15 will be assigned. After that will go to this place, and the digit dot 4 are in the post order direction. Already I explained that post order derivation. But here is we can get the L dot value is equal to 19. So this is the evaluation. Only when you are using the attributes, we are calculating the, you see that the root node value is calculating with the values of its children. Suppose you see that here is t dot value is equal to 15. How you got? So that is here is the, so the t dot value is 3 into f dot value is 5. So then we are getting this. So here is also we are getting this node, but here is e dot value is equal to 19. How we are getting? So that is the left child value is 15 and the right child value is 4, and then that is the operator is plus. By calculating, by adding these two, we are getting this. So this kind of attributes are called the, so that is the yes attributes are synthesized attributes. That evaluation should be takes bottom up parsers as well as post order traversing. I understood that. And the second category, you see that inherited attributes. So inherited attributes means an attribute of a non-terminal on the right hand side of the production is called an inherited attribute. An attribute of a non-terminal on the right hand side of the production is called as a inherited attributes. The attributes can take values either from its parent or from its siblings. So sibling means the siblings, right? So here is, it takes, the node will take the value from its root node as well as its siblings. Sibling means the nodes which are having the same level are called the siblings. So for example, you see that, so that is, let's say A is equal to BC, it has to, BC is a production of grammar, and C attributes is depending on attribute values of A and attribute values of B. That means here is A is computed, so that is the C is computed by evaluating the value of B and by evaluating the value of A. Here is the A is a root node and B is a sibling of this C. Either it may be right or left, but there is some restrictions are provided in the L attributes, right? So this is called inherited attributes. S attributes means the parent will taking values from its children, and inherited attributes means the child is taking the, so that is the values from its root parent as well as its siblings, that is the brothers. So that is evaluation order of this node. Here is whenever are using the same annotated tree, so that is here is the value is missing, that is some value. So that is any SDD with both the inherited and synthesized attributes does not ensure any guarantee order. Even it may not have any order of this one. But here is, but when you are taking the synthesized thing, so it does not provide any rules and regulations. For example, here is, it takes the values from its parent. Here is, you see that the synthesized attributes. Here is, you can call it as a T is a synthesized attribute. But here is, when you are taking that T dot 15, that 15 is so transferring to this place. So suppose here is a 15, and here is also 15 is transferred to this place. So the synthetic value and the synthetic values are this. So next one is, but when you are using the S attributes or inherited attributes, There are no certain rules. So that's why here is we can use the L attributed STD, that is the syntax directed translation. If an STD uses both synthesized attributes and inherited attributes with the restrictions that inherited attributes can inherit values from left siblings only. It takes the values from left siblings only, but not from the right sibling. That is, it is called as a L attribute translated. L attribute translated graph. So that means L attributed means it can, suppose for example in the real life we can take the property from our parents or from our elder brothers but not from younger brothers. So that is the concept in the L attributes means. Attribute is a L attributed STD are evaluated by depth first and left to right parsing manner. That is, here is the evaluation should be done so with the depth first search. That is the depth first search of the graph. Depth first search of the graph we can use, but it is from left to right. So that's why from left to right means, but when you are given that RHS, so for example you see that, suppose if you want to calculate that is the M value, M is depends only on S, but it doesn't depends on N. But when you are taking the N depends on its M value and S value, because so that is the M is the left side child of this. So but here is why M is not taking N means it is a right child of this. But here is a depth first graph can be used for attribution selection, and so there we can use the order of, so the evaluation order of SSDC. So this dependency graph. So the dependency graph is, I think you understood that. So that is the three kinds of attributes. Syntax, so that is the S attributes, inherited attributes and the L attributes. If the value is calculated, so from its children, that is S attributes, value is calculated from its left parent and its sibling, that is inherited, or if we take the parent's node and only left child or any synthesize, it is called L attributes, right? So the dependency graphs we can use, but in the dependency graph, it is a directed graph. So here it will specify the directed graph, it shows the evolution directions of this. So that is evolution order, then you can use the evolution order of this. Suppose here is, for example, you say the dependency graph, the same thing, we already explained that. That is, here is it shows the direction. Suppose if the tree contains any directions, then like this, we can call it as a dependency graph. Dependency graph means graph without cycles is called tree. Generally, we know that graph, acyclic graph means without cycles means that is also nothing but tree. So here is the dependency graphs, you can order of evolution, it will be specified. This is the dependency graph of this. But here is actions, we can see that. And sometimes we can do the action inside the productions. So for every time, suppose if you want to print the values, so for this one, you see the actions. So that is some actions where in the print plus or print, so that is a star. Or here is a print digit value. But when these values will be printing in the graph, this will be specified with the dependency graph. For example, so in this node E, so that is the E contains, so that is the print statement, we can write with the dotted line, that is the print, and E plus T, we are replacing that E plus T, and here is a T, we can use the print star, and here is we can use the print, and at the F we are using the digit and print. So that is all the actions are represented with the dotted line. But how these will be executing, how these will be executing in the S attributes and the L attributes and the inherited. For example, when you are using that, so it uses the topmost, so suppose topmost left direction with the post order. So that means here is the, but when you are using this, so for example, it comes to like this. Suppose here is it is comes to this. So first one, whenever it find that, first that will come to this place, and that place will be printing, or next to that leftmost derivation. So leftmost derivation, first this star will be printing. So after that, so this will be printing. So next that go to this place, and the next that comes to this place, and the digit of this, and this is printing. So after that, whenever that reaches the node, so this print will be, this is the first, second, third, and the fourth time that will be printing. And the next here is after that again that comes to this place. This is the printing, and next that go to this place, and next it is the value of this one. So then here is the first plus will be printing, or next star will be printing, or next suppose in the examination, suppose in the gate they will ask like this. So suppose if you are using the depth first set, suppose depth first sets. So for this one, so then here is, so that is here is whenever the reduction will be done, it will be executed. First leaf nodes. This printing and this value. So suppose here is the value is there. Here is F value. That is the 3 is the printing. Next here is the 5 is printing. After that, this is the root of this. That is the printing star. Or next after that plus is printing, and after that 4 is printing or something. So that is a evolution of the expression. For example, in the same thing we can take the translation. Here is the depth first that will be taking this first print A. It prints the value of A. So after that, that comes to this place, and next the go to the leftmost, that is a B. So next that comes to, so that is this place, and this value is printing, this value is printing, this value node will be printing like this. This is the, so that is the evolution order of these values. So, but I think you understood that. So that is how we are going to translate, and how we are defining the semantics to the, so that is the phosphis or terminals. Applications of this one is, we know that there are main 3 applications. One is the type checking. So second one is the prefix or postfix evolution. I think already I explained that postfix expression. And the next intermediate code generation. So that is in the next session. So this is the next phase. So that's why I will explain that. So in the next session. So now we will see the type checking of this. So suppose here is declaring the data types. D tends to T, ID, D or something. T is a data type. We are defining that T is a data type, and D are epsilon values. Or B and C are record types we can specify. So B is the value integer or float, or we can define the declarations like this. But how do you check the type? Suppose here is I taken this from the net. So then you see that type checking. So suppose here is either the given, suppose in the, if in the expression, so suppose, so when the comparison will be taken, what are the values it will take in the conditional operator? If A is equal to B, that means either, so there the values may be that the output of the relational operator is either 0 or 1, either 0 or 1. 0 means it is true, and 1 means it is false. That means the Boolean values it takes. So second one is, but when you are comparing these two, the data types must be same. The data types must be same. Suppose E1 dot type is equal to E2 dot type. E1 type is integer and E2 type is also must be integers. So here is E can have the form of E1 plus E2. Here is we are writing if statement. If E1 dot type is equal to E2 dot type and E1 dot type is integer, then E dot type is integer, else error. So that means here this is the condition, and the second condition, so that is the expression we are taken, and here is this is the if statement, and the previously I explained that. But here is, so that is E1 is double equal to E2, but here is just only for representing the expression we are taken E1 double equal to E2. Here is if E1 dot type double equal to, and E1 dot type is either integer or Boolean. So then, so that is E dot type is equal to Boolean, else error. So that means here is, first one is the true values must be same data type. E1 dot type is equal to E2 dot type, and the type must be either integer or Boolean. Then only it will get. Then you can use the values. So for this grammar, E is equal to, within the bracket we are using E1, and E number, ER we are framing the values. E dot type is equal to E1 dot type. E dot type is equal to integer. That type is we are declaring that integer. And E is tends to true is a Boolean type data type, or false it is a Boolean type data type. So in this case, for example, if you have taken that, So one example you have taken. So suppose you have taken one example. So suppose here is, so in the bracket, so that is the 2 plus 3. 2 plus 3 is equal to is equal to 8 is equal to 8. Is it true or false? Here is, if you want to see that, you have to see that. So here is the evaluation should be like this. You have to come like this. Int of this values we are replacing. So that is, here is int and number. First we are constructing the tree. We are constructing the tree. So after that the evaluation should be done like this. So here you see that here itself, but when you are using that, here is number is equal to 2. Here is number is equal to 2, and here is the number is equal to 3, and this number is 8. Identifier we are assigned. But these are the integers. Suppose here is, so that is the t dot. So suppose here is in the reverse. That is, here is, suppose when you are using that. So here is, it is a, suppose here is int is equal to, so t dot e. So that is e dot t or t dot e you can use. That means data type. Integer. This is integer type. So suppose this value is replaced with 2. And here is the braces are there. So then here is a plus and this one 3. 2 plus 3 and it will find the values of 5. So here is the 5 is written within the brackets. 5. After that, that will be replacing with the 5. And here is the number is 8 and it will go to this place. And here is that will be checking either 5 is equal to 2. Then, so that will be comes to this place. No, that is the Boolean value. And here is, it will return the false operation. So this kind of type checking will be done for any conditional operator, that is the flow, or so suppose either it will be checked either the integer or character or float like this. So the latter will take the transition diagrams were taken in the regular expressions. So based on that patterns, it will be checking either that is the integer or float or character. Either the given, suppose if the variable is declared the integer, either the value as given integer or any other data type. Or so suppose if you have taken the if-else statement, so then that will be changing. This is the type checking of this one. And print the postfix expression std is equal to scheme. We can use like this and only directly in the print value. So suppose this expression we are written e dot value is equal to e dot value plus t dot value. Later on will go in depth about this, and next that is the, so some, that is the program is also written, that is some procedure we are written for stack operations. So top dot value, top minus 1 dot value is equal to top dot minus. This is the push operation, pop operations, or 1, 2, 3 like this. Based on that we can check the either stack is properly taking the values or not. So that is so these are the theoretical problems, right, in the syntactic analyzers. So now we will solve some gate problems. There are 15 gate questions in the semantic analysis, because it is a, so that is one of the important phase among all the pages for the gate. So here only we are giving semantics to the expressions, right? So up to now what we have studied, that is the annotated tree we have studied. So syntax tree. So next to parse tree, dependency graph, or next to S attributes, L attributes, inherited attributes. So that is the evolution of the construction of parse trees, and some of the applications, that is the type checking, or next that is the stack postfix evaluation. But most of the programming languages, so suppose whenever we are taking that, it will be converted into prefix or postfix. The most of the compilers, the infix expression is converting into postfix, and next postfix evaluation will be done. That's why, so in the data structures we will study the stacks for infix expression to postfix evaluation. So in the postfix, main advantage is, so you need not to bother about the associativity or precedency of operator and braces. That's why you can convert. That is the one of the intermediate form of the language. Now you see that gate questions. So the first question you see that incompatible type. So incompatible type work with the dash. Incompatible. That is the type incompatible. So type incompatibility means, so which one will be checking? As a syntax tree, semantic analyzer, code optimizer, or lexical analyzer. So that means data type checking will be done at the semantic analyzer. Semantic analyzer. That is, so that is the answer is B. Here is for this one, the type checking, giving meaning to the expression. So everything will be comes in the semantic analyzer. So that's why for the question number 1 is answer B. So this is the question numbers, but instead of typing, suppose I have one textbook, so that is on gate, so that is the number of textbooks are there. Just I copy pasted the question, right? But anyways, whether you are understanding or not, that is the important. So generally, you see that question number 2, generation of intermediate code based on an abstract mission model is useful in compiler because, that means generation of intermediate code, but here is sometimes the syntax trees also representing the intermediate form of the language, right? So generation of intermediate code based on an abstract mission model is useful in compiler because. So what is the answer? It makes implementation of lexical analysis and syntactic analysis is the A, and the second bit is syntax directed translation can be written for intermediate code generation. So that is syntax directed translation can be written for intermediate code generation. And the third one is it enhances the portability of the front end of the compiler. It enhances the portability of the front end of the compiler. And D, it is not possible to generate code for real missions directly from high level language to programs. So which one is the correct? So that is here is, so that is a code generation, so that is generation of intermediate code. So with the syntax tree is also a one kind of intermediate code. So representation of one type of intermediate code like this. So but here is, what is the answer? The answer is what? Second question, that answer is, yeah, it makes implement, so that is here is C, that answer is we can use, that is the C. So that is it enhances the portability of the front end of the compiler. Sorry, so that is answer is A. So that is it makes implementation of lexical analysis and syntax analysis easier. Why? Because, so already I explained that. So that is in the first beginning class, the compiler divided into two parts, front end and back end. So that means here is in the front end, so that is the front end is depends on high level language and the back end is depends on mission language. So the main advantage of dividing that into two parts means, so the first part you can implement separately and the second part can implement separately. So that's why, so if you want to make it convenient as a lexical analyzer and syntactic analyzer, so we can use the intermediate code generator, right? But here is separately we can write it the front end and separately we can write it the back end. So for that purpose, here is for the question answer is A. So that is not portability or something. Here is that will be taking. So the main thing is for making flexibility of this. Useful for, because I'm making implementation of lexical analyzer, syntax analyzer is. So next one is the question number 3. A linker is given object model for a set of programs. A linker is given object model for a set of programs that were compiled separately. What information need to be included in an object mission? A is object code, B is relocation bits, B is relocation bits, and C is names and locations of all external symbols defined in the object model, and D is absolute address of, so that is internal symbols. It will add the absolute address of internal symbol. So what is the use of that linker? So it links all the subprograms. For example, the pre-processing, when you are writing the C programs, the libraries will be included, some object things may be used, functions may be included. So that is the use of linkers, right? So that's why absolute address of the internal symbols will be done. It has come in 1995. So that is the answer is the absolute address of internal symbols that will be connected to. Linker is a program that takes one or more object files generated by a compiler and combines them into a single executed program. The linker also takes care of arranging the objects in a program address. Therefore, absolute addresses of internal symbols need to be included in object model. So that's why for this answer is you got that is for 1 mark, it is 1995. Suppose you take the fourth question. In the following grammar, in the fourth question is in the following grammar, x is equal to x plus y, x plus y or y. Y is equal to, that is a z, circle within that y or z. Z is equal to id. So that is, you don't bother about the symbols. Either you can give the plus or minus or you can give any symbols, no problem. Because it is a grammar. So then here sometimes we are using like this. Either exclusive, so suppose XR or something or final set. No, you don't think like that. Only they mention the symbols, right? So which of the following is true? Which of the following is true? So the plus is the left associative, while so that is the star is the right associative in the answer A. B is both plus and star is left associative. So both are left associative. Plus is a right associative while star is a left associative. And none of the above, none of the above. 4 options are given here. So these are 4 options. You see which one is the correct answer? In the derivation part. So what is the answer of this one? Fourth question. That is which one? So that is the blindly you can think that suppose here is that operator is there. So that is whatever the mention the operator, that is the right hand side. So suppose here is they are using this x and x. So that is here is suppose when you are using that. So here is when you are in the y you are using. So that is the y is equal to star like that. Plus is a right associate values and star is a left associate value. So suppose here is derivation should be like this. For example, you see the graph T. So creating syntax tree for that plus identified x star y z is equal to I, and here is x like this. You see that for creating the tree, therefore that is the left associative. Suppose here is when you are saying that, so that is here is that is the left associative. That is the therefore it is a left associative and this is the right associative. For example, you see that answer. Suppose here is, but when you are taking the answer is A. So for example, you see that, but only blindly you should remember that. So that is operator and the symbol. Suppose here is, so in the rule, so suppose the left side operator is in right side, the symbol is there. So then automatically you say that it is a leftmost derivation. That means the derivation should be like left, but when you are replacing the x, it will comes the leftmost derivation. When you are replacing, that is y is equal to z star this. Suppose here is the y is there. So y, when you are replacing that, definitely it will be the rightmost tree you can generate. So that's why you see that here is x. So that is x star. Again you are replacing x into x or x into y or x into y. But whenever that x comes, that will be in the leftmost direction. That is in the, so that is the leftmost derivation. And creating syntax tree for this id and id, just you see that star y z star this one id, and the next again this star y dot this one, because it is in right side. So only blindly you can remember that. Suppose in this case, so that is the left hand side non-terminal is in the right hand side non-terminal. So then either it is it may be before the operator or after the operator. If it is before the operator, So then we can call it as a left associative. So after the operator, you can call it as a right associative. So that's why answer is 4. So answer is A. So the plus is a left associative and star is a right associative. But here is you don't bother about operator precedency. You don't bother about here is a operator precedence. Only the rules of derivation. Rules of derivation. Either so with the given rules, either you can generate the leftmost subtree, leftmost derivation or rightmost derivation. That is the associativity here is calling. Right? So this is the fourth question we are using. I think I have understood that. So that is the question they got in 1997 for 1 marks. But at that time, C. Pascal was there in the 1997. So that's why they are giving questions like that. In 1997 for 1 marks, so they got this question. Suppose same creation, you see that depends on, so ID plus ID. For ID plus ID, we are creating that. For ID star ID, we can create the leftmost. Is it ambiguous grammar or not? You verify it either it is a ambiguous grammar or not. Now question number 5. So consider the translation schema. Consider the translation schema shown below. That is the translation schema means that is a dependency graphs or some translation schema. So that is the below is S tends to TR. S tends to TR. R tends to plus T and some action print plus R epsilon. R epsilon. R tends to plus T. That is some action. That action is a print plus R T epsilon. And T tends to number. T tends to number. It having one action print number dot value. Print number dot value. Print number dot value. Suppose if this grammar rule, if you are given here, so that is what is the answer it will generate for 9 plus 5 plus 2. Suppose if I had given the expression, here number is a token, number is a token that represents an integer and a number dot value representation, the corresponding integer values. That is the number means it represents the number, that is the number dot value. For an input string, you see that for an input string, you see that for an input string, this translation schema will print. This translation schema prints what? What value? Either 9 plus 5 plus 2, A. B 9 5 plus 2 plus, or C 9 5 2 plus plus, or plus 9 5 2. So which is the correct answer? What value it will be. So that is you construct the syntax tree, that is the syntax annotated tree, and evaluate it from top to leftmost directions. And the next is the, for this grammar, test which one is the answer, A or B, C or D. So again, suppose for this one, what is the answer? Just to understand this, here is the grammar you had given, but no operations directly. S tends to TR, R tends to plus T, print of this, but that is the action R slash epsilon. T tends to number, print number dot value. Here number is a token that represents an integer and number dot value represents the corresponding integer value. For an input string 9 plus 5 plus 2, this translation schema will print Answer is, I think answer is P. But how do you calculate? Suppose this has given in 2003 for 2 marks question. So that is in 2003, the question has given for 2 marks. So here is the first you construct the syntax tree. You see that? So answer is we are getting B 9595 plus 2 plus. How you got this one? First thing is for this grammar you have to construct the tree. So that is S is equal to S is a root node, T is the left node and R is right node. You see that T is left node and R is right node. So then here is, so the T, so suppose here is the T is a terminal. Suppose here is the plus operator is there, then you can use the T is a terminal. So that is the terminal value is 9, print 9. So print 9. Here is, we can print number dot value. Number dot value means whatever value you are given in the expression, it assigned to this, it will be printing. Print 9. And we take R. So R can be written plus T. R can be written plus T, print plus. But here is you need not to follow the syntax of the infix notation or something, postfix or something like this. Whatever they are given, just only try the grammar. So suppose for this one, so he has taken the second product, first production of R plus T, print of this R. So then here is the plus T. So for this one, they use the action print. The action statement always represented with dot notation. And next, this T is replaced with the 5. Print 5. So that is a print 5. Some second value, then we'll take a print 5. And the next here is R. Again, R is replaced with the R. So second, again, R is replaced with the R. So suppose second category, you can take the R. So suppose here is R is there, TR. Plus TR and a printf, that is R. So then this R is again replacing with T and R, T and R, because this expression T and A, because every time we have to get T and R. T and R, that is the TR means plus T and the input value of that is 2, print 2, that is a 952. So after that is the print plus, here is the printing plus. And here is R is epsilon. R is equal to epsilon. So that means here is the first we have to construct a parse tree. Have you understood that? How we are creating the parse tree? This is nothing but a postfix. Suppose here is you see that. So then after that, so you traverse the tree like this. Suppose here is a when you are using. So that is the leftmost derivation. You see that like this. Whenever that is reaching, so then print the 9. Next that will come to this place. And the next that comes to this place. That means the first it will print the 9. And the next that is the print statement is here is the 5. So then it print the 5. So there may be chances to get this kind of questions in the semantic analysis. So here is after that, and it will go to this. Or next that is comes to this place, and next it will comes to. So that is here is the 95. Sorry, that is the answer. That is the 9. So that is the value is printing. So for this one, so that comes to this place. So that is the 2. Next to place. And after that, that will go to this. So 95 plus 2, that shows the 952 values will be shown like this. Now we consider that is answer is B for that. And the next you say that sixth question. But here is sometimes it is difficult to understand the question also. Consider the syntax directed definition shown below. So S tends to ID is equal to E. So then here is applied, that is the bottom up parsing. So that's why we got the answer of this. So then here is you are getting this ID. E is equal to generation id dot plus, id is equal to plus, and e is equal to e plus 2. T is a new temporary node generation. T is equal to 1 and t plus 2, that is equal to this one. Hence gen, s here is a gen is a function that generates the output code, and new temp is a function that returns the name of the new temporary variable on every call. Assume that T1 are the temporary variable. So names generated by the new temp. So that is the, for the given expression x is equal to y plus z, then 3 underscore sequence are using this. That's why here they are given for 2 mass. What is the answer? X is equal to x plus y, t is equal to y plus z, t is equal to x, t1 is equal to y, t2 is equal to x plus z, and x is equal to 2, and d is equal to this one. So suppose here is, if you had given that, what is the correct answer for this one? That is in 2003, you had given for 2 marks. It is a intermediate code generation, but I need not to bother about that. The gen function will be used only 2 times. That is x is equal to y plus z, and only one time variable. That is the t is equal to 1 plus z is equal to 1. Only we can, because it is a 3 underscore, later I will explain that because in the next session. T is equal to y plus z we are using, and z is equal to t1. So that's why I can use the answer is B. So now you see the seventh question. Consider the grammar rule E tends to E1 minus E2 for arithmetic expressions. The code generated is targeted to CPU having a single user register. So that is also the, so that in the next session I will explain this, because here is this is the subtraction, that is the code generation is targeted because it comes under the intermediate code. The code generated is targeted to CPU having a single user register. So that means accumulator. Single user register means accumulator. The subtraction operation requires the first operand to be in the register. First requires the subtraction may be first operand. If E1 and E2 do not have any common sub-expressions, in order to get the shortest possible code, that means E should be evaluated first. Answer. Suppose here is you are performing minus operation, that is a subtraction operation. If E1 and so here is only one single register they are using, single register operand. The subtraction operation requires the first operand to be in the register. First you have to show the first register, and if expression and expression 1 and 2 do not have any common sub-expressions, in order to get the shortest possible code. So then here is, so which one you have to execute? That is the T1 should be evaluated first, or E2 should be evaluated first, or evaluation of E1 and E2 should be necessarily be interval. But if you are intervaling two things, two registers are required. Order of evaluation of E1 and E2 is of the no consequences. Then here is, you can say that here is a B. So that means the first this E should be evaluated first. That is the E should be evaluated first. So in this expression, after that we can add that to the second operand. So suppose it is first this will be evaluated and after that. But from the beginning, so we are observing the same thing like this. That's why here is we can use the answer is B. That is to optimize the solution evaluate the expression E2. Then we can calculate E1 and finally E1. So that will be done operation that will be in register. We can perform subtraction directly. But if we follow the opposite, then we will have the value of this. That is the answer is B. Next you see that 8th question. Consider the grammar with the following translation rules. Consider the grammar with the following translation rules, and E as the start symbol. You consider this following grammar. E can have the form of E1 hash T, or another production is slash T. T can have the productions, can have two productions, T1 at the rate of and F and F. to production, F is number. So for this one we are written, so that is the semantic rules. E dot value is equal to E1 dot value star T dot value. So that is the semantic, but only the that value we can add to this. Compute E value for the root of the parse tree for the given expression like this. Here is the 2 star 3 and 5 star 6 and this one. So suppose it is a syntactic tree we have to consider, right? So suppose if you want to execute this expression, how do you execute it? How do you execute and what is the answer for this one? Either 200, 180 or 160 or 40. Then for this one, first we construct the, so that is the syntax annotation tree. Just you see that first we have to construct the parse tree. So that is based on this. We can use these rules. Suppose if you want to find this expression, first we have to use 2 hash 3. 2 hash 3 means E can be replaced with E1 hash T. So then here is E1 hash T1. So then it is annotation means you have to change the T1. Here is the T1 is there. E1 as T1. So that is again E1 is asked to replaced with the star of T. And this one we are repeating number. And next we are also repeating this number. So first whatever here is you have given the string, right? So for this string you try to draw the parse tree, right? After writing the parse tree, so next you assign the values. That is here is you have done the parse tree. So that is the number. That is equal to you are getting the equation for this parse tree. Whenever they are given the string, first thing is you have to construct the parse tree based on the given productions. So then assign the values for the numbers, final F 2, 3, 5, 6, 8. So then you assign the values to this one. Suppose you see that. So suppose here is the first one is we are assigning 2 to here, and that is the 3, and the next one is the 5, and the next one is the 6, and the next one is the 4 we are given. So then here is the same thing we can evaluate from this. So top to leftmost, either it is a top down parser or bottom up parsers like this. So here is you see that here is the number is there. Number is equal to 2 and 2 is replacing this. Next 2 is replacing this, and here is again T2 dot next we are replacing this. Our next one is here is we are replacing with the 6. And after that, so that is this is the evaluation. Number is 3 and here is ampersand and here the number is 5. This will be executing and this will be executing like this. For example, here is you see that, but sometimes just only, so this is replacing, but you see that hash is here is replaced with the star. Hash is replaced with the star, and ampersand symbol is replaced in the plus. So I have understood that clearly. That is what is the difference parse tree and syntax tree. But here is hash, that may be any general operator, but here is you have to use the star and here is the others. That's why here is. So when you are evaluating the values like this, suppose whenever taking the values of this one, so it will be calculate and the other two, so suppose here it will take the A dot value, calculating that values will be taken like this. So then here is when you calculate this T, so like previous value, so then you can get the answer is 180. Answer you can get the value is 180 like this. I understood that. But when you are given the expression, that is so whenever you are given this thing, but the first thing is you should construct the parse tree. You should construct the parse tree. 2 as 3 at the rate 5 as 6 and this one. So first you construct the parse tree. So after that you make it as a, here is the grammar as given. This is the context free grammar. This is the context sensitive grammar. So it is a so that is the context free and context sensitive grammar. So first for this one we are deriving the graph by producing the thing. But here is you can get the ambiguous grammar, no problem. Suppose if 2 or 3 trees may be there, but you choose any tree. But in the semantic analysis, definitely you have to follow the rules. That's why you can get the correct answer, no problem. So that is, you can take the top-down approaches or bottom-up approach parsing techniques. You can get the answer, correct answer of this. This is the one. I think you understood this. So that is in 2004. They are given it for 2 marks. 2004. So this question was given for 2 marks. So that's why here is the construction, parse tree construction is a very, very important. Either you can follow the top-down approach or bottom-up approach, no problem. So, but here is construction. The most of the cases we are deriving by the top-down process, right? So for the execution of this, so that you can get the answer is like this. So next another question you see that consider that is, this is second time I am explaining this. Consider the grammar E tends to E plus N or E into N or N. Here is the 3 productions are there. For E, there are 3 productions, E plus N or E into N or N. So, but here is they are given question. So, suppose here is, so the problem may be different. For example, you see that they are given string N plus N into N, N plus N into N. For the sentence N plus N into N, the handles in the right sentential form of the reduction are. So that is in the right handle in the right sentential form. Right sentential form is, so you have to construct the tree in the with the right mode derivation in the reverse order. Right mode derivation with the reverse order. So which is the correct answer? For 9th question, the answer is I think D. So suppose you see that answer is D. Here is we are taking answer is D. So how we are getting that answer? Suppose here is if you want to derive the string, so first we can take that is E is the root. E is the root. After that we replace that with this production, so that we can get this string. And next after that we can replace the second production, right production, that E into T, for getting this production. So that is the next, the value is replaced with the N. So I answer that. Yeah, consider the grammar E tends to E plus N or E into N or N. For a sentence N plus N into N, the handles in the right sentential form of the reduction are. So suppose when you take this one plus or this one, here is the 2 productions are coming, or here is suppose the first production is this, and the extra values we are getting here. But here is we are getting the correct sentence of this tree. Only with the 2 productions we can get the answer. For example, you see that, so that D is the answer. So that is E tends to E plus N or E into N or N. This is the grammar, right? So then here is when you are using this grammar, so this is the grammar we are using. So input string N plus N into N. So this is for construction of this input, either you can construct the parse tree or directly we can evaluate the regular expression. Suppose here is expression, so N plus N into N. So then here is, suppose here is taken that in the reverse direction, suppose in the bottom of parsers we can use. But here is taken that he has used in the bottom of parser. Or otherwise you can use the top down parsers and you can derive it. So for example, here is when you are taking this N into N plus 1, here is top down parser you are applying. So suppose first N is replacing with E, that is the reduction. So that is the N is replaced with E, because here is, so that is the N is the answer. And next reduction. So N is Rama Nikla. Open the door. So that is the reduction E. So suppose the next one is E. So suppose E plus N. Here is you see that E plus N is there. This production is used for reduction of this one. So then we are getting E into N, and here is we are getting N. So the reductions are, so first what we have done, first we have reduced the N, right, or next to N E plus what's N, compare. So that is the E into N, right? So answer that the evolution procedure. So this is the LFD. And the next 10th question you see that. So that is this kind of questions they can ask from the semantic trees. So consider the following translation scheme. Consider the following translation scheme. S is equal to ER. R tends to star E. Print star R slash E. E tends to E plus E tends to F plus E. Print plus R F. F is equal to within the brackets S. R ID print this value. That means here is 1, 2, 3. 3 actions are there. Then consider this following this, and here ID is a token that represents an integer or ID dot value. Here this ID represents the integer value. The corresponding integer value. So that is for an input 2 star 3 plus 4. 2 star 3 plus 4. This translation scheme prints. What is the value it prints? What value it prints? 2 star 3 plus 4. This translation scheme prints. The answer is A or B or C or D. This is a question given in 2006 for 2 marks. That means most of the cases from the semantic trees are very, very important. So for this one also, first you draw the semantic tree, that is a parts tree for this one. Just a parts tree. 2 star 3 plus 4. 2 star 3 plus 4 but the stream. So you have to find the calculate. You have to calculate the value of this. Generally you see that first construction of parts tree. S is a root node, E and R. So we are taking S is a root node, E and R. And the next E is replacing with F, is replaced with F. So that is F tends to E plus R and F is there. So that is in this case, so that is E is replacing with so second production of this F, and F is equal to ID, that is equal to 2, and next to print 1. So there is the print value. So that is equal to print 2. Or next that is same thing we are constructing into R is replaced with star E and R. So then here is R production is replacing with the star E of this one. So because here is the printing star E or E into R. This is the one expression. You see that? So this is our output. This one is up to this is the one production, right? Up to this one is the one production. Don't think it is a 2. Then up to this one is a one production. So then we are replacing and construct the tree. So when you are evaluating this like this, first this will be executing, printing, and the next 2 will be printing, next 3 will be printing, next what? So that is the 3 will be printing, next what here is then we are using the star will be printing, third case, and the next where is it? So that is the print and that comes to this one, printing of this one, print of this. Suppose here is when you are using this. So, but when you are printing like this, you have 2, 3, 4 plus and star. You can get the answer is suppose 2, 4 plus, that is answer is D. Right? I answer that. Answer is D. Then you see that here is we are using printing 2, right? Printing 2, and here is a printing 3, and here is a printing 4. Next after that here is a star is there and plus is there. So there is a first inner line. So then it is a star is printing. After that, first plus is printing and star. You see that only difference is so that is in the depth first searching, right? So that is the leftmost and the depth first. So then here is that will be printing the values of this. Leftmost and the depth first values. Here is from this leftmost, first to this one, you see that all are, so next from this, that comes to this place, and then next this one. So after calculating this one, that will come to the root node. So after the printing this, next go to this and go to this place of this. So there is a 2, 3, 4 plus and star. But most of the cases, the people will think that here there is a one confusion is there. So this is we can say that it is a postfix notation. Most of the people will think that actually it is a postfix. That is, we can think it is a answer is C. So that is answer is C, but actually answer is not C. That is answer is D. So then here is for this one you have to construct the notational tree, and then you have to use the values of this. And you see the 11th question. This is also very, very important. In 2011, they had given it for 2 marks. They had given it for 2 marks. Then you see that consider 2 binary operations. To consider 2 binary operators. So that is the arrow, top arrow and down arrow with the precedence of operators. So that is the down arrow being lower than that of the operator higher precedency. That is the top precedency. This will be having top precedency. This will be having the lower precedency. Operator T is a right associative. That is so the top direction operator is a right associative, while operator down is a left associative. Which of the following represent the parse tree for expression? Parse tree for this expression. For example, here they are given expression. You see that here they are given expression, right? So they are given expression of this. So for this expression, so actually what is the condition here? One is the up arrow is there, one is the down arrow. Down arrow having the lower precedency than up arrow, and that is the up arrow is having the right associativity. That means that will evaluation should be from right to left, and down arrow means that is the evaluation should be from left to right. So when you are drawing this, what operation you can get? For example, you see that. So when you are getting the first one is what? Down, and left tree is what? 7 you got. Here is you got 7, right? So next it is a what? It is the direction. Next we are taking that. The next symbol is what? Up arrow. Up arrow means that will come to the right directions, right? So next here is when you are taking that. So then here is the left to right. So suppose here is again up, and here is the down is there. You see that here is the down arrow. Down arrow means it should be the right side, but actually this is not correct answer. And but here is in B you see that it is a down arrow means, so that is the left side, that is the down, and for this left side it is a right side. So for this line here is we are getting right side, and here is the right side. So here is, suppose when you see that, so that is the B is the correct, and you see that here is also down arrow, again down arrow. Down arrow means it should be the what? Left associative. That means it start with the left side instead of the start with the left side. And all of these are correct, but here is this is started with the right side, so it's not a correct. Here is also this is the down arrow, so that is the down arrow means next is these are the up arrows and higher precedency. It will make a right tree. So suppose for this one you have to draw the right tree like this. That's why. So that is A is not correct, C is not correct, and D is not correct. Only that B is correct answer. Just you see this, but so that is the only precedence is based on the precedence. Here is also nothing but you have to draw the false trees. Then you see that answer is B. That is the down arrow, and the next one is having down arrow. That is the left associative. For this one, up arrow is there. For this one, it will come to right associative. For up arrow, for this one, this is the right associative. Suppose when you come to the left arrow, again that will come to this place. So next we consider this question, 12th one. So consider the expression shown below. Each leaf represents the numerical value which can either be 0 or 1. Overall possible choices of the values of the leaves. The maximum possible value of the expression represented by the tree. Suppose this is the tree at E, so that is in 2014 and set 2, they are given it for 2 marks. So here is, so in this case there is a 0 or 1 or 0 or 1, 0 or 1, 0 or 1, 0 or 1. In each leaf node I can take either 0 or 1, but at the top most you have to get the highest value. So that is you have to get the highest value. What is that highest value you can get here? So that is the question. You see that? So the leaf nodes is either all leaf nodes that can 0 or 1 or 1. So for example, here is, you see that. So how do you get it? So suppose here is a 1 and a plus is there, right? So suppose you take that is a 1. So 1 plus 2 side 2 this when we are taking that, you can get the 2. Here is the answer is 2 we can get. But here is the minus is there. Suppose if we are taken here is the 1, 1 minus 0 is 1 we can get. Or suppose 0 minus 1 means we are getting minus 1. So the minus 1 means it will be reducing. So that is we can't get the maximum value. So that's why here is from this we can take that is a 1 minus 0 that is equal to 1. So here is you can get the maximum value is we are getting 1 itself. And here is a 2 plus 1 that is equal to 2 minus 1 that is equal to 1 we are getting. So that is 2 minus 1 is equal to 1. Or next here is suppose it is 0 minus 1 or 1 minus, the same thing here is so that is a 1 minus 0 we can take. So that is equal to 1. The plus means 0 1 or 0 1 that is equal to 2 here itself. So that is 1 plus 3 or something like this. Suppose you see that. So here is you have taken the minus 1. So 1 minus 1 is a 2 and minus 3. So that is a minus 1 plus that is equal to minus. So that is the, but when you are taking, here is you have taken the 1 minus, suppose 0 minus 1 because here is the minus is there. Minus plus minus is 0. Then you see that here is you have taken the 1 and 1. So 1 plus 1 is the 2. Here is you can get the maximum value. But here is you take minus 0 minus 1 is equal to minus 1 and 1 minus 0 is equal to 1. But before that here is the minus is there. So that's why here is, so that plus 2 plus minus of minus 2 that is equal to minus of minus 2 that is we are getting 3. Note of this. And the next here is, so next one or same we are repeating and we are getting answer is 6. We are getting answer is 6. Minus of minus means 2 like this. So next 13th question. I think this is the last one. Yeah. So 13th question. One of the purpose of using intermediate code in a compiler is to make parsing and semantic analysis simpler, improve error recovery and error reporting, increasing the chances of reusing the mission independent code optimization, other compilers, and improve the register allocation. But here is, you see that the question is that the C is the correct answer. One of the making parsing and the semantic analysis is simpler, not for this one, and that is the intermediate code. Here is so, but depending upon the options, somewhere it may be correct, or but somewhere it may be. But because based on this 10 of 4 multiplications, you have to increase the chances of reusing the mission independent code optimizer in the other compilers. That is the compilers we are using like that, right? So these are the so answer is C. So they got question in 2014 set 3 or mass of this one. But in the recent questions, right? So this is the code generator. So that is the syntax tree. So that is the semantic analysis phase. I think you have understood, right? So I think more. So that is the 2 hours of time. So thanks for your patience. Hmm? So if you have any doubts, you can ask me, right? So thank you. So that is after this you practice on the semantic analysis. So that is my slides are available in the website. So then you go through the slides and videos, and so that I hope good luck for this. Right? You practice it. Suppose whenever they're getting the questions, input string, construct the path tree, construct the mediated tree, and try to evaluate this either in the postfix notation, that is the top down parser. I apply the bottom up parsers. Then you can use the values of this. So thank you. Thanks for your patience. I hope you understood everything. Thank you, Amma. Thank you. Hello. Yeah, shall we close it?